I welcome you all for the GATE online lecture Casting Part 2. I am Dr. M.S. Vallavi, Assistant Professor in Mechanical Engineering, Government College of Technology, Coimbatore. The content of this lecture: types of casting process, gating system, shape and riser size, solidification and cooling, casting defects, and gate question and answer with discussion. First, we will see about the types of casting process. Types are investment casting, shell mold casting, centrifugal casting, die casting, permanent mold casting. In investment casting, molten metal is poured into a expandable ceramic mold. The mold is formed by using wax pattern, a disposable piece in the shape of desired pot. The pattern surrounds are invested into ceramic slurry that harden into the mold. Investment casting is often referred to last wax casting because the wax pattern is melted out of the mold after has been formed. Last wax pattern are 1:1, which increase production time and cost relative to other casting process. However, since the mold is destroyed during the process, pot with complex geometries and intricate details can be created. This is the investment casting process. We have patternry, then shell making process. After shell making, the molten metal is poured into the cavity, and finally we are getting the casting product. Pattern creation. The wax pattern are typically injection molded into a metal die and are formed as one piece. Cores may be used to form any internal features on the pattern. Mold creation. This pattern tree is dipped into slurry of fine ceramic particles coated with more coarse particles and then dried to form a ceramic shell around the pattern and gating system. This process is repeated until the shell is thick enough to withstand the molten metal. Pouring. The mold is preheated in the furnace approximately 1000 degrees Celsius and the molten metal is poured from ladle into the gating system to fill the mold cavity. Cooling process. After the mold has been filled, the molten metal is allowed to cool and solidify into the shape of final casting. Cooling time depends upon the thickness of pot, thickness of mold and the material used. Casting removal. After the solidification and cooling, we have to remove the casting. We have to break it and casting will be removed. Finishing. Finishing operations such as grinding or sandblasting are used to smooth the pot of the gate. Heat treatment is also sometimes used to harden the final part. Advantages of investment casting. Just for complex shapes and fine details, high strength pot we can get. Good surface finish and accuracy we can obtain from this investment casting. Little need of secondary operation. Disadvantagement is a time consuming, high labor and tooling cost, long lead time will be there. Applications: turbine blades, pipe fitting, lock pots, hand tools and jewelries, etc. Next process is shell molding. Here we have to make a shell. By using the shell, here we are in the shell we are pouring the molten metal and what are the shape of shell we are getting the product like as this shell. Similar to sand casting, in that molten metal is poured into an expandable mold. In shell mold casting, the mold is thin walled shell created from applying a sand resin mixture around the pattern. The pattern, a metal piece in the shape of desired pot, is reused to form multiple shell mold. So it is It can be reused, so this comes under expandable mold. A reusable pattern allows for higher production rate, while disposable molds enables complex geometries to be cast. Shell mold casting requires the use of metal pattern, oven, sand resin mixture, dump box, and molten metal. So these are the things required for shell molding. So we have dump box, sand resin. The pattern is there. The here the required shell we can get. Okay, here ejector pin. This is the cross section of the shell mold. Then this is what the final product. Pattern creation. A two-piece metal pattern is created in the shape of desired part, typically from iron or steel. Mold creation. First, each pattern half is heated to 175 to 370 degrees Celsius and coated with a lubricant to facilitate removal. Next process, the heated pattern is clamped to dump box, which contains a mixture of sand and resin binders. Then the dump box is inverted, allowing this sand resin mixture to coat the pattern. Then the heated pattern partially cures the mixture, which now form a shell around the pattern. Each pattern half and surrounding shell is cured to completion in an oven, and then the shell is ejected from the pattern. Mold assembly. The two shell halves are joined together and securely clamped to form the completely shell mold. If any cores are required, they also insert period to the mold closing. The shell mold is then placed into the flask and supported by the backing material. Then pouring, we have to pour the molten material into the shell using ladle. After that, we have to allow for cooling and solidification. Then we have to remove the casting from the mold. After the molten metal has cooled, the mold can be broken and the casting removed. Advantage of shell molding. Complex shapes and fine details we can get. Good surface finish. We can obtain high rate of production. Low labor and tooling cost. Little scrap generated. Disadvantage, high equipment cost. Applications are cylinder heads and connecting rods, etc. Centrifugal casting, sometimes known as rotocasting. It is a metal casting process that uses centrifugal force to form cylindrical part. This differs from most metal casting process which use gravity or pressure to fill the mold. In centrifugal casting, a permanent mold made from steel, cast iron, graphite is typically used. However, the use of expandable sand mold also possible. The casting process usually performed on a horizontal centrifugal casting machine and vertical machine also available. So this is what the centrifugal casting setup. So we have the rollers. We have rollers here, and here we have mold, and motor will rotate. So we are pouring the molten metal here by using ladle, and this will be injected into the mold. So this motor is for creating rotary movement, and this is what the pouring basin here, and we are getting the finished casting. Mold preparation. The walls of a cylindrical mold are first coated with the refractory ceramic coating, which involves a few steps, that is application, rotation, drying and baking. Next process, pouring. Molten metal is poured directly into the rotating mold without the use of runner or gating system. The centrifugal force drives the material towards the mold walls as the mold fills. Then cooling. Cooling begins quickly at the mold walls and proceeds inwards. Casting removal. After the casting has cooled and solidified, the rotation is stopped and the casting can be removed. Finishing. While the centrifugal force drives the dense metal to the mold walls, any less dense impurities or bubbles flow to the inner surface of the casting. The result is secondary processes such as machining, grinding, sandblasting are required to clean and smooth the inner diameter of the pot. Advantage: can form very large pots. Good mechanical properties we can achieve due to centrifugal force. Good surface finish and accuracy. Low equipment cost, low labor cost, little scrap. Disadvantages are limited to cylindrical pots. Secondary machining is required. Long lead time. It is applicable to for making pipes, wheels, pulleys, nozzles, etc. Next type of casting is die casting. It produces geometrically complex metal pots through the use of reusable molds called dies. The die casting process involves the use of furnace, metal die casting machine and die. The metal, typically non-furnace alloy such as aluminium or zinc, is melted in the furnace and then injected into the die in the die casting machine. We have two types under the die casting: hot chamber, cold chamber. In hot chamber, which is used for alloy which low melting temperature such as zinc. In the cold chamber machines, used for alloys with high melting temperature like aluminium. In both the machines, after the molten metal is injected into the die, it rapidly cools and solidifies into the final pot called the casting. Clamping. The first step is the preparation and clamping of two halves of the die. Each die half is first cleaned from the previous injection and then lubricated to facilitate the ejection of next pot. Injection. The molten metal, which is maintained at a set temperature in the furnace, is next transferred to the chamber where it can be ejected into the die. The method of transforming the molten metal is depend upon the type of die casting machine, whether a hot chamber or cold chamber machine is being used. Cooling. Next cooling process. The molten metal that is ejected into the die will begin to cool and solidify once it enters into the die cavity. When the entire cavity is filled and the molten metal solidifies, the final shape of the casting is formed. The die cannot be opened until the cooling time reaches. Ejection. After the predetermined cooling time has passed, the die halves can be opened and an ejection mechanism can push the casting out of the die. Last one is trimming. Excess material is removed in this stage. Next one is permanent mold casting. It's chassis similar to both sand casting and die casting. As in sand casting, molten metal is poured into mold which is clamped shut until the material cools and solidifies into the desired shape. However, sand casting uses an expandable mold which is destroyed after the heat cycle. Permanent mold casting, like die casting, uses a metal mold die which is typically made from steel or cast iron, can be reused for several thousand cycles. Because the molten metal is poured into the die and not forcibly injected, permanent mold casting is often referred to as the gravity die casting. So this is what the setup. We have the here the mold half is there, and we have the core pin, runner, screw. So another half, we have two halves. Then core pin is there, and we are pouring the molten metal through this, and we are closing that. Finally, we are getting the final product like this. Mold preparation. First, the mold is preheated to around 300 to 500 Fahrenheit to allow better metal flow and reduce defect. Mold assembly. The mold consists of at least two parts. The two mold house and any cores used to form complex features. Such cores are typically made from iron or steel, but expandable sand cores are sometimes used. In this step, the cores are inserted and the mold house are clamped together. Then pouring, we have to pour the metal at slow rate from the ladle into the mold. The mold metal flows through the runner system and enters the mold cavity. Cooling, we have to allow the molten metal for cool and solidification. Mold opening, after the metal has solidified, the two mold halves are opened and the casting is removed. Trimming, the excess material is removed in this process. The advantages are it can be used for complex shapes. We can attain good mechanical properties. Many materials we can use this. Low porosity, low labor cost. Scraps can be recycled. Disadvantages are high tooling cost, long lead time. Applications are gears, wheels, housing, engine components we can produce by using this permanent mold casting process. Next, we are going to discuss about the gating design. A good gating design should ensure proper distribution of molten metal without excessive temperature loss, turbulence, gas entrapping, and slack. If the molten metal is poured very slowly, since time taken to fill the mold cavity will be longer, solidification will start even before the mold is completely filled. This can be restricted by using superheated metal, but in this case, solubility will be a problem. If the molten metal is poured very fast, it can erode the mold cavity. So both the case we have some problems. Types of gate. Vertical gate. The liquid metal is poured vertically directly to fill the mold with atmospheric pressure at the base end. So by the atmospheric pressure, the material is filled in the mold cavity. This is what the mold cavity here. So we are pouring the material. So it will come into this screw and it will fill the mold cavity. So the total height is from here to here. This is total. This is the pouring basin height and this is the screw height H2. The velocity of the flowing molten metal increases towards the base of screw. Air can be aspired into the liquid and taken into the mold cavity. To prevent this condition, the screw is designed with taper so that the volume flow rate remains the same at the top and bottom of the screw. Mold filling time. From this mold filling time, TF equal to V by Q. That is P is the volume of mold. That is A is the cross section area of gate. P3 is the velocity at screw base. This is the mold filling time. T equal to volume of mold divided by discharge. So Q equal to area into velocity. Another type is bottom gating. This molten metal is poured from top but filled from bottom to top. This minimizes oxidation and splashing while pouring. So if we are pouring the molten metal from the top, then it enters. Then first it fills the bottom, then top portion is filled. So this is what the total height, screw height. This is the mold height. So after this it is filled. AM and AG are mold area and gate area. So here mold filling time TF equal to AM divided by AG 1 by root of 2G into 2 into root of HT minus root of HT minus HM. So HM is here, H total is here, and AM is the mold area, AG is the gate area. So from that we can find the mold filling time for the bottom gating system. Horizontal gating is a modification of bottom gating in which some horizontal portions are added for good distribution of molten metal and to avoid turbulence. Shape and riser size. The risers are designed to solidify last so as to feed enough metal to heavy section of the casting to make up for the shrinkage before and during solidification. For this, they should lose heat at a slower rate. Amount of heat is proportional to the volume and the rate of heat dissipation depends upon the surface area of riser. The surface area should be designed with a high V by A, that is volume by surface area ratio for given size. This will minimize the loss of heat so that the riser will remain hot and the metal in the molten state as long as possible. This condition can be met when riser is in spherical shape. The surface area is minimum that time. The next best shape is cylinder. As riser of ideal spherical shape are difficult to mold, consequently the cylinder is the best shape to employ. Height of the cylindrical race can be calculated as 1.5 into diameter of the riser. Rectangular sections are very inefficient and must be avoided. So the best sections are spherical and cylinder. Cylinder we can select for all the purpose. It is best. Riser size. Riser size can be calculated by using Chevroni rule. And this we can find the solidification time or freezing time. That is T equal to C into P by SA, that whole square. V is the volume of casting. SA represents the surface area of casting. C is the constant, depend upon the composition or properties of the cast material, pouring temperature, mold material, etc. The metal in the riser must be last to solidify to achieve directional solidification. Normally, V by, that is volume by surface area of riser is larger when compared to the volume by surface area of casting. Then we have another formula for riser size, Keynes formula. Riser size is based on experimentally determined hyperbolic relation between freezing time and volume of casting and the riser. Here freezing time represented X. X equal to surface area divided by volume of the casting divided by surface area by volume of the riser. Volume of casting Y, which is equal to volume of the riser divided by volume of casting. In Keynes formula, X equal to A divided by Y minus B plus C. Here A is the freezing characteristic constant, B liquid solid solidification contraction, C relative freezing rate of riser and casting. Next one is solidification and cooling. Solidification involves the transformation of the molten metal back into the solid state. It differs depending on whether the material is pure element or an alloy. If metal is pure metal solidifies at constant temperature equal to its freezing point, which is the same as its melting point. Here we can see the graph. So this versus temperature and time. Temperature versus time. Here this is what the pouring temperature. Then after time goes, the temperature comes down. So cooling starts. Then it comes down. And here the freezing begins. Okay. And here temperature is constant. And after time goes, freezing completed. Okay. Then again is cooling up to solid state. Okay. From freezing begins to freezing completed is the local solidification time. From pouring temperature time to the freezing time, it is known as the total solidification time. Starting from pouring time up to the freezing time, completion of freezing time. That is known as the total solidification time. The actual freezing takes time called local solidification time in casting, during which the metal latent heat of fusion is released into the surrounding mode. The total solidification time is the time taken between pouring and complete solidification. After the casting has completely solidified, cooling continues at the rate indicated by the downward slope of the cooling curve. Because of the chilling action of the mold wall, a thin skin of solid metal is initially formed. Thin skin of solid metal is initially formed at the intersurface immediately after pouring. The metal which forms the initial skin has been rapidly cooled by the extraction of heat through the mold wall. This cooling action causes the grains in the skin to be fine and randomly oriented. Okay, randomly oriented. As cooling continues, further grain formation and growth occurs in the direction away from the heat transfer. Since the heat transfer is through the skin and mold wall, the grain grows inwardly as needles or spines of solid material. As these spines enlarges, larger branches form, and as these branches grow, further branches from at right angles to first branch. This type of grain growth is referred to the dendritic growth. And it occurs not only in freezing of pure metal but alloys as well. So this is what the grain structure in casting of pure metal. It shows the randomly oriented grains of small size near the mold wall. So these are the small size near the mold wall, which is randomly oriented. And large column grains, these are the large column grains oriented towards the center of the casting. Towards the center of the casting. Solidification and cooling of different material. Cast structures of metal solidifies in the square model. First diagram shows the pure metal. This for pure metal. So this is the chill zone, columnar zone. So what we discussed here. So we have the randomly oriented structure here, and we have the columnar zone here. Then second one is the solid solution alloys. So here also we have the equiaxed zone here. So the structure. And the third one is the structure obtained from heterogeneous nucleation of the grains using nucleating agent. So here we can easily visible the equiaxed structure here. full of eq-axis structure. Here the center only we are getting this eq-axis zone structure. Next we are going to see about the casting quality defects. First one is misrun. This is the unfilled region exists in the mold. This is due to the insufficient fluidity of metal, low pouring temperature, slow pouring, cross section too thin. So unfilled region. So up to this the material should fill, but it is not filled properly. That is known as misrun. Next one is cold shut. Premature freezing at fusion point. Okay. Premature fusion. So here it is not filled. Okay. Similar reason as misrun. Improper fusion of two streams of liquid metal. Cold shoots. Splattering during pouring, forming solid globules. So globules are formed. Redesign of pouring procedure or gating system is needed. Shrinkage cavity. Depression or internal voids caused by solidification shrinkage. So this is for the shrinkage cavity. Solved by proper razor design. Microporosity. So the small pores are there throughout the mold. Network of small voids caused by localized solidification shrinkage. This caused by freezing manner of the alloy. Next one is sand globe. Cavity caused by mold gas during pouring. So this is the cavity. Low permeability, poor venting or high moisture content. Because of that this will produced. Then pinhole, small cavities. Okay, that is what pinhole. Then sand wash. So this is what the sand wash. Erosion of sand mold during pouring. Scab. Mold surface locally flask off and embedded in the casting during solidification. Next one is penetration. Penetration of the molten metal into the sand. Order packing of the sand is needed. Mold shift. So this much here. Shift of the cob relate to the drag. Then core shift. Okay, it is not in center. This shifted upwards. Okay, this eccentricity is the shift of the core, usually vertical. Mold crack. Mold strength is insufficient. Liquid metal form a fin of the final casting. Then blowholes. Blowholes are smooth round holes that are clearly perceptible on the surface of casting. It occurs when the excessive evolved gas is not able to flow through the mold. So it is densely packing of the sand. So gas will not escape. To prevent blowholes, moisture content in sand must be well adjusted. Sand of proper grain size should be used. Ramming should not be too hard and venting should be adequate. Last one is hot tear. Hot tears or internal or external rack discontinuities or crack on the casting surface caused by rapid contraction occurring immediately after the sand solidified. So this is what the hot tears or cracks. They may be produced when casting is poorly designed and abrupt sectional changes takes place. No proper fillets and corner radius are provided and chills are inappropriately placed. Chills for proper solidification. Incorrect pouring temperature and improper placement of gate and races can also create hot tears. Resolved by mold collapsing or removing from the mold immediately after freezing. These are the casting defects. Now we will discuss about the gate question answer. First question is match the product with manufacturing process. Automobile piston aluminum alloy, engine crankshaft in spherical graphite, carburetor housing in aluminum alloy, casting titanium blades, pressure die casting, gravity die casting, sand casting, shell molding. So automobile pistons are normally done by gravity die casting. Then engine crankshaft is by means of sand casting. Then by sand casting. Then carburetor housing in aluminum alloy, that is done by pressure die casting process. Then casting titanium blades are made by the shell molding process. So answer is A. Next question is cubic casting of 50 mm side undergoes volumetric solidification shrinkage and volumetric solid contraction of 4% and 6% respectively. No razor is used. Assume uniform cooling in all directions. The side of cube after solidification and contraction is. So this is what the question given to us. Side of cube, let we will take it as A, which is 50 mm. Volume of cube, that is V. Volume of cube V, that is A cube, that is 50 cube, that is equal to 125 3 zeros mm cube. In the question, they mentioned that first cube undergoes the volumetric solidification shrinkage by 4%, then it undergoes volumetric solid contraction by 6%. Okay, so cube first undergoes volumetric solidification shrinkage, that is 4%, and then it undergoes the volumetric solid contraction of 6%. Okay, first now we have to find out the volumetric volume after shrinkage. For that, V1 equal to 1125 3 zeros, okay, minus volume after shrinkage. Now we are going to calculate. So original volume is 125,000. Now volumetric shrinkage that we have to take it into account, that is 125,000 into volumetric solid solidification shrinkage is given as 4%. 4 divided by 100. So we are getting 12 4 zeros. metric cube. In same manner, we have to calculate the volumetric contraction also. Volume after contraction. First, we are calculating the volume after shrinkage. Now, this is what the volume as of now. 12 4 zeros minus here solid volumetric solid contraction 6%. That is equal to 112800 mm cube. Okay. Now V2 represents the combined volume after volumetric shrinkage and contraction. Now take cube side as B. Initially we are taking the side as A. Now we are taking the side as B. So now we are getting the total volume. This B cube as 112800. From that you can get the side of cube, that is 48.32 mm. This is what the answer. 48.32 mm. Okay. Next question, we have match regarding casting defect. In group A, we have a hot ears, shrinkage, mold holes, cold shirt. In group B, improper fusion of two streams of liquid metal, low permeability of the sand mold, volumetric contraction both in liquid and solid stage, different cooling rate. So here hot ears is due to the differential cooling rate. Okay, then shrinkage is the contraction, volumetric contraction. Then blowholes is due to low permeability of sand. And the cold shirt, that is for improper fusing of two streams of liquid metal. So B is the answer here. Hot ears, it is a metallurgical defect and occurs because of differential cooling rate, which creates stress in the different region of metal. Shrinkage, it is a volumetric contraction as volume reduces during cooling. Blowholes, this is due to permeability of sand mold. Cold shirt, due to improper fusion of two streams of liquid metal. Next we have a problem. The solidification time of casting is proportional to V by A, that whole square, where V is the volume of the casting and A is the total casting surface area lost in heat. Two cubes of same material and size are cast using sand casting process. The top face of one of the cube is completely insulated. The ratio of the solidification time for the cube with top face insulated to the other cube is. This is what the question they are asking. Here one cube is insulated, one face is insulated, another cube is not insulated. So based upon that we have to calculate the ratio of solidification time. Now we will see solution. First, we have to find out the surface area of first cube, which lose heat from all the surface. So it lose heat from all the surface. So it is a cube. So surface area is 6a square. Next, we have to find out the surface area of second cube, which lost heat from 5 surface, because one surface is insulated. Okay. Insulated. So this 5a square. Now ratio of solidification time or freezing time, which is equal to T insulated divided by T uninsulated. So for T we have formula, that is volume of the casting divided by the surface area of the casting, that whole square. This is for insulated divided by V by A whole square for not insulated case. Okay, non-insulated. So volume of the insulation is A cube divided by surface area of insulation is, the surface area of insulation is, one side is insulated, so here surface area is 5a square. Whole square divided by non-insulated, volume of the cube is A cube divided by, since it is non-insulated, the surface area is 6a square, that whole square. So this can be written as A cube divided by 5a square into a square divided by b cube, that whole square. This will be cancelled. Finally, we are getting 6 by 5, that whole square. This 36 divided by 5. Here we go. Here A represents the side of cube. Now answer is 36 divided by 25. This is what the answer. Okay. Next one is again we have match in defect. Blowholes, Mishran, hot tears, wash. Poor collapsibility, mold erosion, poor permeability, insufficient fluidity. So answer is D. So blowholes, that is for poor permeability. Then Mishran is due to insufficient fluidity. Hot tears, that is for poor collapsibility. Wash for mold erosion. Okay. Then we have another problem. A mold cavity of 1200 centimeter cube volume has to be filled through a screw of 10 centimeter length feeding a horizontal runner. Cross-section area at the base of the screw is 2 centimeter square. Consider acceleration due to gravity as 9.81 meter per second square. Neglecting frictional loss due to molten metal flow, the time taken to fill the mold cavity is. Okay, this is what the question. Pouring basing, screw. Here we have runner. This is what the mold cavity. So volume of the mold cavity given and area of the screw, cross-section area of the screw is given here and screw length of the screw also in the question. Now we have to calculate the time taken to fill the mold cavity. First we will take the given volume of the mold cavity, that is given in the question, B equal to 1200 centimeter cube. So we will convert this into meter. Then height of screw is given. This 10 centimeter, which is equal to 0.1 meter. Cross-sectional area of screw. Two centimeter square is equal to 2 into 10 power minus 4 meter square. Then G is given 9.81. So since height of the screw basin is not given, so assume height of screw basin is not given, so assume that it can be neglected when compared to the height of screw. Okay. Now velocity of molten metal. Molten metal at 3, that is this is 1, this is 0.2, This is 3. Okay. Area is 2 centimeters square. That is sprue area. Then this is 1200 centimeters square. This is what the mold. The height is given here. Height of sprue. This is equal to 10 centimeter. Height of the pouring basin is not given. Okay, that we neglected. Now velocity of molten metal at 3. Okay, at 3. That is 3 point is end of the sprue or at the entrance of the gate. You can take it as two sense. So this is the end of the sprue or entrance of the runner. Okay. So now V3 equal to root of 2G H. Since it is the sprue side, we are taking like this. So 2 into 9.81 into H is 0.1. So we are getting 1.4 meter per second, V3. Next we have to calculate the flow rate. Flow rate of molten metal is equal to area of the sprue at the point 3, then velocity is equal to 2 into 10 power minus 4. Velocity is 1.4 meter per second. So now the discharge is, that is flow rate is 2.8 into 10 power minus 4 meter cube per second. Then now we want to know the time taken to fill the cavity. So I will write here. Time taken T equal to volume divided by flow rate. Okay. So volume of the mold is this T equal to 12 into 10 power minus 4 divided by flow rate is 2.8 into 10 power minus 4. So we are getting T as 4.285 seconds. Okay. This is what the answer. First we have to calculate the velocity. From that we can calculate the flow rate. So this is what the formula. Time taken T equal to volume divided by flow rate. Volume of the mold divided by flow rate, that is Q here. And while substituting that, we are getting the T. Okay. Time taken to fill the mold cavity is 4.285 seconds. That is, they are asking 2 decimal round off, so it is 4.29. Okay, next one is hot tears in metal casting is due to high fluidity, high melt temperature, wide range of solidification temperature, low coefficient of thermal expansion. Answer is C, wide range of solidification temperature. because hot AS in metal casting is a metallurgical defect which is also called hot cracking, which occurs as the casting cools. This happens because the metal is weak when it is hot and residual stress in the metal can cause the casting to fail as it cools. Proper mold design prevents this type of casting so that the uniform cooling rate for all pots can be maintained, which reduce the range of solidification. So, due to that, answer is C, wide range of solidification temperature. Next, we have another problem. Figure shows the pouring arrangement for casting of a metal block. Frictionless losses are negligible. The acceleration due to gravity is 9.81 meter per second square. The time to fill up the mold cavity is. So here they gave the volume of the casting. So this is the atmospheric pressure, diameter of the sprue, open to atmosphere. This is what the mold, rectangular mold. So the total height they gave 20 centimeter, including the pouring basin. So from that we have to find out the time to fill up the mold cap. Okay. So here given us that is V equal to 40 into 30 into 15 is equal to 1830 centimeter cube. Then total height is 20 centimeter. Pouring basin plus screw height 20 into 10 power minus 2. Enter. Then G is given 9.81 per second square. Then diameter of the sprue. What is it? Filling height diameter is diameter of the sprue given 2 centimeter. Okay. Here also we have to calculate the velocity of molten metal, that is at 3. Okay, velocity of molten metal at 3 we have to calculate. That is the end of sprue or entrance of the runner, right? At 3 we have to calculate. That is velocity equal to root of 2gh. Here we have to take as a total height 2 into 9.81 into height is 20 centimeter. Just 1.98 meter per second. Then time taken to fill the mold cavity. That is T equal to volume divided by Q. That is volume of mold divided by flow rate. So now we have to calculate the Q, which is equal to A3V3. That is area equal to this cylindrical portion, so it is area square. So it is 3.14 into 1.98, and then we can get 6.22 into 10 power minus 4. So now we can calculate the time taken to fill the cavity. So volume divided by flow rate. Here volume is given in the question 1830, that we have to convert it to meter divided by 6.22 into 10 power minus 4. Okay. So the time taken is 3. This is what the answer for this question. So time taken is V by Q. So V is the volume of mold divided by flow rate. Flow rate we can calculate it by using the formula Q equal to area into velocity. Velocity is equal to root of 2gh. Okay. Next one is in which of the gating system molten metal flows into mold cavity due to the adverse effect of gravity. Okay. Answer for this question is bottom gate. In top gate, limited to relatively small casting of simple shapes. So it is limited to the simple shapes design. The turbulence, this is the main problem. In bottom gate, it reduces the turbulence and erosion of the mold to a minimum, but creates the unfavorable thermal gradient. So we have to select the bottom gate. So next question is ratio of solidification time of cylindrical casting, height equal to radius, to that of cube casting of side 2 times the height of cylindrical casting is ratio of solidification time of cylindrical casting to the cubic casting. Okay, in cylindrical casting, height equal to radius, cubic casting, side equal to 2 times the height. Okay, now they are asking the ratio of solidification time for the cylinder and cube. So, in cylindrical casting, here what they give, height equal to radius. So we know that solidification time G equal to constant into volume of mold divided by surface area of the mold, that whole square. So here volume divided by surface area of cylindrical casting, which is equal to volume of the cylinder is pi r square h divided by surface area is 2 pi r square plus 2 pi r h. Since they are giving in the question h equal to r, so we have to replace r with h, which is equal to pi h cube divided by 2 pi h square plus 2 pi h square, which is equal to h by 4. This is for cylindrical casting. For cube casting, what they gave is side. Side is 2 into h. Okay. Here also we have to calculate the volume divided by surface area. This is equal to a cube divided by 6a square. Since a is the side of cube, then a by 6 is equal to a equal to 2h, 2h divided by 6, so it is h by 3. Now Now we want to know the ratio of solidification time. So solidification time of cylindrical casting divided by solidification time of cubical casting. Okay, that is T cylindrical divided by T cube, which is equal to C into volume divided by surface area square of the cylinder divided by C is the constant, volume divided by surface area of the cube, which is equal to V by surface area of the cylinder is H by 4. Okay. Volume by surface area of the cube is H by 3. That we have to substitute H by 4 into H by 3, that can be written as 3 by H, that whole square. That is 9 by 60, which is equal to 0.565. This is what the answer for this question. Solidification ratio of solidification time of the cylinder to the cube is 0.5625. Okay. Next question is, racer is designed so as to freeze after the casting freezes, freeze before the casting freezes, freeze at the same time as the casting, minimize the time of pouring. So we know that racer should freeze after the casting. This is what the right answer. Next we have another problem. A cylindrical racer of 6 cm diameter and 6 cm height has to be designed for a sand casting mold for producing a steel rectangular plate casting of 7 into 10 into 2 cm cube dimension, having the total solidification time of 1.3 minute. So total solidification time of racer. Total solidification time of racer they are asking. They give the total solidification time. Okay. So here given that is volume of mold 7 into 10 into total time is equal to 1.36 minute. We want to know the total time of riser, and they gave the diameter of the riser 6 centimeter, height of the riser also. Okay, so we know that solidification time T equal to constant volume divided by surface area whole square. For steel plate, that is solidification time. Total solidification time is 1.36 minutes. Now we want to know the volume of steel plate, which is equal to 7 into 10 into 2 centimeter cube. Then surface area of steel plate, which is equal to 2 into 7 into 10 plus 10 into 2 plus 2 into 7. Okay. Next we want to know the basic volume and surface area. That solidification time of riser we want. So volume of riser is equal to pi by 4 d square h squared into 6. Then surface area of riser is equal to pi by 4 square plus pi into 6 into 6, that is 2 pi r into r plus h. So here I take it as diameter. For rectangular plate, the formula is 1.36, which is equal to C 1 into 10 into 2 V by volume divided by surface area of the plate. The first equation. Then riser into surface area of the riser. So this is equation 2. From first and second equation, we will get solidification time of riser 1.36 into from that we will get the answer. Yeah, it will be okay. Here we are calculating the volume for volume and surface area for rectangular plate and riser. From that we are solving the equation 1 and 2. Finally, we are getting the solidification time of riser. Okay, time of riser. So summary of this lecture is, we saw the different types of casting process and casting design, shape and riser size, solidification and cooling, different defects comes under casting, and we solved problems, and these are the reference. Happy learning. Thank you.